Yeah, thanks for the opportunity to be here. Actually, I was trying to find ways that I could bridge what Jeff was saying with what I'm saying, and I came up with a few. Actually, I'm going to talk a little bit about some trends in consolidation of content and the internet infrastructure, and with regards to social networks. I previously worked at an infrastructure security company, and a lot of stuff like tracking botnets and malware and helping people mitigate attacks. And my daughters would ask me how, what I did and what it was I actually worked on. And like, all right, whatever, Dad. And so now I just recently moved to VeriSign about 5 months ago, and we operate some of the registries and .com and .net and so forth. So my daughters were asking me what I was going to be doing there, and I said, well, a lot of the same stuff and some new things, but we actually operate these internet registries. Like, well, that's cool. She basically didn't care much about it. I was like, well, we make all these online social networks like Facebook.com and Twitter.com. Those things wouldn't work if our infrastructure didn't work. And she said, well. It's like, yeah, that really doesn't mean anything to me, Dad. So she didn't care, right? She didn't care. And it actually has a lot to do with what I'm going to talk about today, is a lot of the things that enable the infrastructure, things like the domain name system and a .se and what that actually entails, how that, these sort of, the veiled risks associated with those. People don't sort of enumerate or think about the, what enables them to access the content that they actually desire. And so I'm going to talk a little bit about that. I actually have a longer session this afternoon in attack vectors, where I'm going to talk about a lot of stuff related to infrastructure security and security trends as well. So anyway, that said, we'll jump right into this. So I'm going to share a couple of primitives of the internet architecture first, and then then we'll step into some changes that are occurring with those and why those might be challenging. So if you sort of step back, the internet's a collection of loosely interconnected networks, right? Of global loosely interconnected networks, and there's no single authority, there's no single point of control on this network. It's datagram or packet based, and what we mean by that is that information's chopped up into little pieces, and it's sent out into the network to find its way to the destination. And each piece of data, each one of these datagrams, has destination information on it. So you could liken it to an envelope on a letter, and they put the envelope on there and they say this is destination, and they put it in the system, and it somehow magically finds its way to the other side, to the destination, right? And there are some things that enables. And then one of the ultimate goals in designing packet or datagram based networks initially when they were being researched was end-to-end, any-to-any connectivity, meaning I put something in an envelope and I send it off to the destination, and the destination gets it, and nobody in the middle needed to look at the contents of that or to understand the contents. And so there's this sort of layered model actually provides some scalability. The network's dumb and the edges are smart, and it enables innovation. And so that's some of these sorts of things is what has actually allowed IP and the internet to be so successful today. So some really high level bits. If you think about some of the primary infrastructure elements. You ask me as sort of a routing and network and security guy, I think about DNS and routing and IP and so forth. And a name is where do you want to go? What's your sort of navigation anchor, if you will? And then the address is where it is on the infrastructure. What's it mapped to? Where am I actually going? And then the route is how to get there. And so the DNS and the IP namespace and the addressing infrastructure is extremely important. And then BGP, or the internet routing system, is how you reach a given destination on the internet. Some of the primitives this enables are, you get these sort of systemic threats because of the way the infrastructure works. There are some, the IP network itself is very resilient, and you get this end-to-end, any-to-any connectivity with lots of resiliency. But at the same time, there are these hierarchical overlay systems. So, for example, DNS is one such example, I guess, is that while I could reach someone in the same state or the same country, I may not be able to reach them unless I resolve a DNS query on a network somewhere else in the world. And so DNS and these infrastructure enabling protocols must function before I can get that user desired content. And that's really important. Asymmetry of threats, I'll talk about a little more in just a moment. And then the complexity and attribution. From a security perspective, one of the challenges with the internet is anybody has sort of global reach or global projection capability. And so, when you think about everything from cybercrime to cyberbullying to cyber terrorism, the full spectrum, attribution is really, really difficult to see who launched an attack or who was responsible for, some malicious activity, or see if someone's credentials were compromised. Was it really the person that said they did that? So anyway, when you ask most people about the internet, if you ask my daughter or your average internet user, the internet looks a lot like this, right? It's you sort of got a disk drive on the other side of their broadband connection, and they think that all the content they want to access is on that big disk drive. And there aren't any variables, right? But the reality is that a lot of the content you get isn't local to you. It may even be global on someone else's network. But again, before you can access that content, you have to go, resolve, for example, DNS transactions or certificate status queries or that sort of thing, maybe on 10 or 15 or 20 different networks before you can actually get the content that you want. And if those infrastructure enabling or supporting transactions don't resolve correctly, then you can't get the content you want. So it's really critical that that infrastructure be available on the back end. So the internet protocol model, what's it look like? This is what I was talking about a moment ago. And this is sort of the layered architecture of the internet, right? What you see on the two sides is you got a user, in this case, an application that's a web browser. Could be an email client, could be anything. On the far side, you got a web server, an email server, something like that. And you have this layered network architecture. So it's end-to-end, any-to-any. And when I say end-to-end, IP sort of sets at layer 3, or what we call the network layer. And every device from the end systems, from this laptop to the wireless access point, to the router, to the intermediate devices, to the server on the other side, have to support IP at the network layer, right? Or IPv4 in this case, and we're going to talk about just for a moment about IPv6 in a bit. And then at the layer below that, you have things like radio and fiber and Ethernet and 3G and so forth that are providing what you call the link layer and the physical layer substrate. And then above it, you have the applications. The applications are are sort of what benefits most from the network externality or the network effect, right? So you got user groups on the internet that drive things and enable, social networks and so forth. The challenge at the network layer is that most people don't see that. It just enables the infrastructure and the connectivity. So that's sort of the layered model. What this allows you to do is those intermediate devices in the network don't have to be as sophisticated. If you thought about sort of the postal system again, and you sent that envelope, and you put your letter in there, and you sealed it, and you put the destination address on it, and sent it out in the network. If you assume that the Postal Service had to open that envelope and read the contents of that to decide where it should go or how it should be processed in the system, it obviously wouldn't scale very well. And so that's sort of what you're looking at here is those intermediate devices in the network. Don't look at the payload or the contents of the infrastructure generally, and so that allows you to get end-to-end and preserves privacy and other functions. What do I want to talk about here? So one of the other points that I'm going to talk about some is that because this is end-to-end, each device on the network requires a unique identifier, an IP address. Today it's IPv4, and IPv4 traditionally provided about 4 billion IP addresses, 4 million unique identifiers on the network. Well, given that there are 7 billion people in the world, and some folks project that in 2 to 4 years that a single individual may have 16 IP addresses themselves, or 16 different devices that have IP addresses. That's obviously a challenge. So we're actually, the IPv4 address space is quickly depleting, and within the next year, at the root of this allocation hierarchy for IPv4 will be fully depleted. And so IPv6 is sort of the next set of address space there, and it has 340 trillion addresses, and so it should be a bit more sufficient at the end of the day. So. All right, so I'm going to share a couple of stats. If you look at textbooks or anyone taking a computer science network engineering course, the old internet looked like the one on the left, where you had a very hierarchical structure and a couple of folks at the top. But the reality is that today it looks a lot more like the one on the right. The internet's much, much flatter. To illustrate this, it's grown over an order of magnitude in the last 10 years from the number of participating networks, that loosely interconnected set of networks that make up the internet. But the diameter from one AS to, from one network or routing domain to any other one on the internet has actually shrunk over time. And so, the result of that's because networks are much more densely interconnected. And so, that has lots of effects, right? I mean, that provides robustness in the infrastructure. It helps that IP resiliency, the end-to-end model, if the transactions and what you're actually looking for are as equally resilient. But when you look at content consolidation, back to some of Jeff's point, what you actually see over the last few years is a significant consolidation of content. What you're looking at here, this is called a CDF, or a cumulative distribution format graph. And basically, the takeaway here is that in 2007, about 1,500 ASs made up for 50% of the content on the internet. And in 2009, it's only 150. About 30 networks on the internet account for about 30% of all internet traffic. And to see how that's evolved, you see Google and Comcast there. Actually, I was reading a blog post from some of my ex-colleagues at Arbor yesterday or this morning, I think. And Google is actually number 2 now with about 6 or 7% steady state of all internet traffic, one organization, right? So that has some significant implications on everything from privacy to user tracking to to policy and regulatory issues. What else do we want to say? So, so I guess, when you have this, the fabric of the network is much more densely interconnected, but content, what people want to access is much more consolidated, then you have these reliability issues that may emerge. If that site's not available, what's that mean to your average user on the internet? Another example, actually, is Indian. So we were talking about Indian. Traditionally when IP was designed, if you knew the destination IP address of some place on the internet, you simply put your envelope, you put your letter in your envelope and sent the envelope to into the network, and it found its way to the destination. And they opened it, right? Well, you could use any protocol, any language you wanted, do anything you wanted inside the envelope, essentially, right? Well, with security in particular, a lot of folks block everything, for example, but web ports or email ports and so forth. So in order for application developers or people that want to innovate on the internet, instead of just putting it in in a standard IP packet and sending it to some destination on the internet. Now what they do is they say, well, I'm going to put it in the web port because the web port's going to have a hole in a firewall and let me reach the destination more efficiently. So this bottom right graphic here, there's something known as sort of the IP hourglass model. And basically that IP, that network layer, is the thin waist of the hourglass. And it's starting to look more like what you see in the diagram now, where most of what goes over the internet is actually tunneled in TCP port 80, or the web port, so that it can find its way through a firewall. And that's not necessarily a good thing. We're losing some of the transparency end-to-end on the internet. So some other things, so IPv4 depletion and IPv6 deployment I was talking about. One of the challenges with this, and why it's important, if you're not looking at IPv6 already and you have anything to do with the network, you should be. The reason it's important is because IPv4 and IPv6 are what you call bits on the wire compatible. So if you have an IPv4 laptop and an IPv6 laptop on the same network, they can't speak natively to each other. They have to have some translation function. And so this is a challenge. The deployment model for IPv6 was everybody's going to run IPv4 and IPv6, and then when we get to that state, we'll turn off all the IPv4. And that was 15, 20 years ago. And today we don't have enough IPv4 to accommodate what we call a dual stack deployment model. And so that's a challenging challenging transition plan. But as I noted earlier, that the top of the hierarchy for address allocation of IPv4 addresses is going to be exhausted within a year, and then the regional registries, in this case, right primarily for Sweden or the European region, is just subsequent to that. It's within operational time frames, so you definitely need to be looking at IPv6 in your infrastructure. Routing on the internet. Routing on the internet operates in a manner that I call routing by rumor. And basically, if you recall earlier, routing is how you get somewhere on the internet. So I send a packet in the network and it magically finds its way to the destination, all right? Well, the reality is that this routing protocol, the Border Gateway Protocol, sets up that reachability. And what I do with the Border Gateway Protocol, BGP, is I announce in the internet, I assert reachability for some set of destinations. Well, there's no central authority or no sort of authoritative source that says who holds what number of resources on the internet. And if you don't have that, you can't secure the routing system. But if you have that and you use it to secure the routing system, then that's another dependency that doesn't exist in the system today. So you have to balance those things and figure out how to best balance autonomy that you may want to gain with the security of the system. Essentially, today in the routing system, pretty much anybody that has access to a BGP speaking router, an internet router, can assert reachability for anyone else's address base. And we've seen a lot of incidents related to this. I think Curtis may actually be talking about some of that later in his talk. Some of the other things, most of your user desired transactions, if you want to go to Facebook, what do? The very first thing your client does is resolve www.facebook.com to an IP address, right? And how does it do that? It uses DNS, the domain name system. And then it reaches out to the local recursive name server, which hopefully is on the same network. Then it reaches, if it's not cached in that server, then it reaches out to a root name server, then to a top-level domain server, and then to a second-level domain server that's probably Facebook.com's, right? Well, those are three different iterations and about 4 or 5 transactions potentially that enable that. And a lot of times those servers don't actually sit on the same network, and they could be multinational. And if any one of those in that sort of resolution chain break, then the user can't get to the content they desire. And so you have to enumerate that and consider that as part of your operational surface or attack surface, if you will. Certificate status, certainly you have to be able to resolve certificate status if you're doing secure transactions. And a lot of times the content you want to access may not be local or within some area that, it's not that disk drive at the end of your broadband connection. It's, some remote place on the internet. Okay, so the DNS landscape, if you ask me what it looked like from a high level right now, I'd say it looks like you got money over here and you got knowledge or truth or integrity on the left side, right? And in between somewhere, it's like, well, which way do we go with this? So everybody's like, hey, we got DNSSEC, and it gives us integrity in DNS. And on the other side, you got people that use either rogue DNS resolvers if you're a miscreant and want to compromise end users or phish sites, or you want to do botnet if you're an ISP. Maybe you want to do botnet quarantine or walled garden functions, or maybe you want to do NX domain mapping and generate search revenue from your subscribers if you're an ISP, or you want to implement parental controls for your users and so forth. And so, on the other side, that's all about not telling the truth in DNS, right? So DNSSEC's about integrity, and there are things that can bring you, like new applications with carrying certificates or other data you may want to have in the DNS. But on the far right side, it's like, hey, here's the money, and it doesn't involve integrity. So that's a challenge. So finding ways to balance integrity and the authenticity of data in the DNS with the contrasting desire for capitalist markets, I guess, and operators to make money is challenging and something we're going to continue to struggle with. Reactive control. So I slid this slide in the deck because it's pretty important for people to understand this. Basically what you're looking at here is this bottom right graph, this triangle, is sort of network layer. That's IP if you recall the internet layered model. And then up the stack is applications. And basically the wider the triangle gets there, the more vulnerabilities you see. If you look at the number of vulnerabilities that saw exploits last year, in other words, the piece of malcode on the internet that existed, there's a new piece of malcode every 10 seconds, more or less, right? Literally every 10 seconds. And our number one defense to protect against this is antivirus software, IDSs, right? Well, if there's a new piece of malcode every 10 seconds and I update my antivirus software, my IDS once a week or once a day or whatever it is, and on average those signatures are 2 weeks old, I'm probably not protected all the time, right? As a matter of fact, if you take the top 10 antivirus engines and you squished them all together and said, what's the result I get for protection? It's about 80 to 90% on average, best case, right? And on average, if you just take one, you end up with about 60 to 70% protection against the unique threats on the internet. And anybody in here that's a security person realizes you have to be right all the time. The miscreants only have to be right once. So what you're saying is 9 out of every 10 transactions you're reasonably secure on the internet, but 1 out of 10 you're not. And every time you go on the internet, there's a million transactions and you don't know what 500,000 of those actually are because you don't see them, then it can be challenging. Digital immigrants. So I read this term actually in this Internet Security Alliance brochure. It was talking about how to talk to a CFO about cyber risk, and they had the notion of a digital immigrant. It was a person that that didn't grow up with with an Atari or with an internet connection or any kind of compute capability whatsoever. They printed out things or had their admin do that and so forth, and they didn't really understand even any network-based risk, much less dependencies that may exist somewhere else in the world, right? So they don't have a problem investing in a countermeasure or control or safeguard that might put out a fire suppression system or a backup power supply for something or physical security in a data center. But if you tell them they need redundant DNS servers or they need DDoS protection or they need spam mitigation capabilities or there are these threats somewhere else on the internet that they have to deal with, then they have a hard time investing in that. And so until these digital immigrants sort of realize that the risk associated with what they care about most, the assets, their online presence and availability, are entirely reliant upon the availability of all these supporting protocols and transactions, then it's going to be really challenging to get the proper investment in protecting those assets. Some spaghetti. So basically here, if you're not preparing for IPv6, you're already behind. It's within operational timeframes, and you definitely need to be looking at that. Within a year, it's, the address base is going to be exhausted. The number certification resource repository, it's kind of interesting to think that on the internet today there exists no formally verifiable database that says who holds what IP addresses. We have integrity in DNS now, and DNS maps a name, a human readable, a human readable name to an IP address, but we don't have an authoritative database that says who holds what number resources. So absent that, you can't really rely upon that IP substrate entirely until you have that capability. So we definitely need resource certification, and some work's happening around that. DNS landscape's challenging. It's kind of interesting if you think about DNSSEC. It brings integrity to DNS, but if you look at sort of the 3 pillars of information security, you have confidentiality, is it secret? You have availability, can I access it, and with some reasonable performance, and you have integrity. And DNSSEC brings integrity to DNS, but it is more resource intensive, and it requires extra capacity and extra resource and state and CPU cycles and so forth. And so, you're trading off availability to get integrity in the DNS. And so, what does the integrity bring you? So if you looked at that spectrum earlier, it's like, what do I gain by having integrity in DNS? And the reality is that you gain the ability to connect with confidence to where you're going. So you have to secure the substrate first. What else do we want to say here? So compliance, one of the things that I think is really interesting, I do a lot of security stuff, and you get compliance, and compliance usually trails reality by 5 to 10 years. And if you look at sort of the threat landscape, and most of what compliance aims at today, it's a couple things. It's like firewall that blocks everything but TCP port 80. It's antivirus software, and it's disk encryption, right? And if you look at threats today, it's like, well, all the threats and all the compromises are client-side infections, so they work right through a firewall and right through TCP port 80 and probably right through your web proxy. Your users get compromised, but you have a firewall there that maintains state, and it's a middle box in the network, and it compromises that end-to-end thing that we care a lot about. As a matter of fact, it usually becomes the bottleneck when there's a denial of service attack because it maintains state in the middle of the network, and it opens up those envelopes, and so it often fails in that case. Antivirus software, it's like you got to have AV. I mean, and AV actually does raise the bar, but you're not protected all the time with AV, right? Don't assume that because you have AV, you're not vulnerable. You need to make sure that you put other countermeasures or protections in place. And then disk encryption, it's useful, but most of the time, if somebody has access, if they've compromised your machine, then they probably have access to whatever it is, to the credentials you use to encrypt the disk anyway. So. What else do we have? So, the internet's at an inflection point. The internet's really always at an inflection point, I guess, but there are a lot of new technologies that are, they're sort of reshaping the internet. And a lot of convergence. You see a lot of other protocols now. A lot of the traditional siloed networks like frame relay and ATM and voice and video and all those sorts of things are carried on IP networks now. When you carry those things, you converge those things on an IP network. They inherit the entire attack surface of every layer in that layered protocol model below them. So you have to emulate their essential attributes or whatever they required, but at the same time, they have this new attack surface that they're now captive to. And so you have to understand what enables that infrastructure below them. And if it's DNS or a routing update or an IP address, you better make sure that you have some security and adequate capability with that. All right, so end-to-end, is challenged. A lot of people want to use things like, well, IPv4 and IPv6, because they're not bits on the wire compatible, there's capability for that to fragment or partition, pieces of the internet, and we definitely don't want that. The reason why the internet's been successful is because of end-to-end, any-to-any connectivity. DNS is the same, right? If you use DNS as a policy enforcement function in a recursive name server, an authority zone, or on an end system, then you're going to fragment. You're not going to have a unique global namespace that resolves the same to all users. And that's challenging, right? That's basically fragmenting or partitioning the internet. Multidisciplinary systemic approaches. One of the things I'm going to talk about this afternoon is a lot of people look at an attack surface, even if you're looking at DNS attack surface, and you see 1 or 2 elements, not all the elements involved with that. And, and there are all these systemic elements that start all the way with the meat computer, right? The guy behind the keyboard that's, that's inputting all the stuff. If he's in some way compromised or his credentials are compromised, it doesn't matter what other safeguards you might have in place. And then finally, one of the things I had mentioned earlier is I don't know how many folks in here have heard about something like a CISSP, right? But it's basically a security certification you can get. And one of the things they teach you to do is be pragmatic. When you go in an organization, talk about what the most critical asset to that organization is. And for most of the people in this room, it probably has something to do with network or availability or online presence or so forth. And And so when you look at the valuation of that asset, you know, don't just think about investing in power supplies or circuit redundancy or fire suppression systems. Think about what enables that asset or that availability on the internet. And it's probably got something to do with routing and DNS first and foremost, these infrastructure enabling protocols. So you have to fully enumerate what enables that infrastructure, that asset that it is you're looking to protect, and then what countermeasures you might invest in to protect that asset. So anyway, with that, I know I probably moved fairly quickly, and my English, well, I speak fast enough anyway, but I hope most of you actually speak some English. If you don't, then you might want to look at the slides, and you missed everything, but with any luck, you can at least go look at the slides, and this was remotely useful. So again, I thank you for the opportunity to be here today as well. So,
thank you.